Okay, so my presentation focuses on mining and mine waste impacts on groundwater flow systems. So by the time I arrived, the groundwater research group was fully developed, and it was a really rich environment to do graduate studies. So we had people with expertise in hydrogeology, geochemistry, modeling, and then aquatic geochemistry, soil physics, and biogeochemistry. And Bob Farvolden had expertise in water resource management. John Frape and Ed Sticky joined later, and John Greenhouse was a key component of the group, but unfortunately I didn't put his picture up. So I'm talking about mining. Mining directly impacts Canada's GDP. It's about 6% of our GDP and 21% of our imports or exports. Most of that is metals. And it directly employs 430,000 people. There's about 200 active mines in Canada and far more inactive mines, or decommissioned or closed mines, or abandoned mines. So both cause environmental concerns. The environmental concerns range from catastrophic tailings dam failures, like the one at Mount Poly in 2014, which released tailings to Lake Quesnel. But a more insidious and ongoing concern is the release of acidic drainage containing high concentrations of dissolved metals. So mining generates a variety of waste. So the mines themselves that are causes or sources of contamination, then waste rock that's derived from the mines in order to access the ore, and then the tailings derived from concentrating the valuable minerals from the ore, and then the refinery wastes, and then metal finishing wastes. All in all, copper production generates about 99 tons per ton of waste per ton of copper, and when you go to things like gold or diamonds, that waste ratio gets much worse. Mine wastes are the largest volume of earth material that's moved in the world. In Canada, we produce 300,000 tons of waste rock per year and 700,000 tons of tailings, and that's about 30 times the volume or mass of domestic and industrial waste combined. So the processes that drive the acidification of water in mine waste systems are the oxidation of sulfide minerals. In this case, it's pyrite, which reacts with oxygen in the presence of water to generate ferrous iron, sulfate, and hydrogen ions. It can re-oxidize that ferrous iron to form ferric iron, which can also oxidize pyrite to generate further sulfate, ferrous iron, and hydrogen ions. Or it can go to precipitation of iron oxides, like this is goethite, which generates additional ferric hydrogen ions. So oxidation can be by oxygen or by ferric iron, and all these reactions are kinetically limited, but there's always bacteria there that accelerate the reaction, so they proceed as quickly as the reactants are supplied. So these are a couple types of mines. This is an underground mine at Red Lake, in the Campbell Red Lake mine in Bombertown, Ontario. So there's a couple of head frames you can see here, and there's one off in the distance, and there's a tailings impoundment in the background here. This is the Kennecott, Utah copper mine near Salt Lake City. It's about 4 kilometers across and about 1 kilometer deep. You can see this haul truck here on the ramp within the mine. Waste rock piles are large. So this is the waste rock pile at the Diavik Diamond Mine in Lac de Gras in the Northwest Territories. So the rock from the open pits has ended up in the waste rock pile that's here. So that's about 1.5 kilometers long and about 200 meters thick or high. So tailings are the fine-grained residual. So the precious metals or valuable metals are extracted either by gravity separation or differential flotation. At times, they're roasted to drive off sulfides to release things like gold. They're fine-grained sand or silt size, and they're typically high in iron and pyrite and pyrite, which are the iron sulfides which have little value. So the work on mine waste at Waterloo started at Elliott Lake in Ontario. And this is a picture of the Nordic uranium mine and mill, and off to the side you can see the Nordic tailings. This is a picture from a postcard that I bought about 40 years ago. So the ore at Elliott Lake is Precambrian sandstone. So there's detrital deposits that are derived from before the atmosphere was oxygenated that contain uranium and pyrite. The ore is crushed and then hot acid leached, and then the uranium is extracted by solvent extraction, and the tailings are then neutralized with lime before they're deposited in the tailings impoundment. So the resulting waste is about 90% quartz, about 5% sulfides, and less than 1% carbonate, so it's strongly acid generating. So the concerns are acid generation and radionuclide transport. Prior to my arrival, this tailings impoundment was being studied. When I got here, Dave Smith was studying the unsaturated zone, or the Vado zone. Neil Dubosky was studying the saturated zone, and Kevin Morin was studying the aquifer and the connection to the surface water flow system. So there's oxidation occurring in the Vado zone that was releasing acidic water with high concentrations of dissolved metals and sulfate. The acid was being neutralized within the tailings, but the high concentrations of ferrous iron were moving along the groundwater flow path and exiting into, in this case, a drainage channel where there's oxidizing and causing acidification. So the combination of these studies really developed the paradigm for acid-generating mine tailings systems. So in my PhD work, I expanded this to three mine sites. One in New Brunswick was a zinc-lead mine, a copper-zinc mine in Quebec, and a gold mine in Timmins. We had a variety of different tools that were developed. So dry point piezometers were developed here at Waterloo, and bundle-type piezometers that can be installed in drill holes. And we use suction lysimeters for extracting water from the Vado zone. We've made a variety of field measurements, pH and EH and electrical conductivity, pore gas, oxygen, and CO2 concentrations, lots of different spectrophotometry methods in the field. And this is Chris Hanton-Fong doing some sampling in the field. So in those days, our tools were pretty crude. We had a flame AA for analyzing cations. So we could analyze one cation at a time, and we recorded our data with a pencil and paper. We did anion chromatography, recorded on strip charts, so you could pick off the height of the peak on the strip chart, or Eric Riordan would cut out the strip chart to be much more quantitative than the rest of us were. We had a lot of different colorimetric techniques, and our microbiology was by culture-based techniques. There was excellent staff. We had Paul Johnson and Bob Ingleton in the groundwater research lab, and Ron Kellerman and Tracy Fowler in the geochemistry lab, which really made things nice. And as always, the isotope lab was excellent. We had almost no microbiological tools here. We had optical microscopes, or transmission and reflected light microscopes. There was an old SEM in mechanical engineering, and we had an X-ray diffraction unit which didn't work and was a hazard. Luckily, in my first year as a PhD student, I encountered John Jambor, who was a mineralogist from the Mineral Sciences Lab at CanMed in Ottawa, and he really upped our game in terms of mineralogy. So I worked with him for more than 2 decades after that. So if you look at the Delnite tailings impoundment, it has about the same sulfide content as the Elliott Lake tailings, but the carbonate content is much higher. So as a result, the drainage is neutral, and we don't see very high concentrations of dissolved metals, but we do see high concentrations of arsenic. So this is concentrations of iron versus depth. So iron concentrations are about 2 orders of magnitude lower than we see in Elliott Lake, but the arsenic concentrations are up to 6 or 7 milligrams per liter, which is more than 1,000 times the drinking water quality limit. We see arsenic accumulating in rims surrounding, this is a pure-type grain, and this is arsenic that's accumulated within that rim surrounding the grain. So not all of the arsenic is in the water, a lot of it's in the solid phase and eventually will be mobilized. In New Brunswick, we looked at the Heath steel ore body that was studied previously by Borman and Watson from the New Brunswick Research and Productivity Council, and that's about 85% weight sulfide and much less than 5% carbonates. And the drainage is highly acidic and very high concentrations of metals. So we see pHs at the surface of down to as low as 0.5, and concentrations of iron up to 50 grams per liter and sulfate up to 100 grams per liter. See up to 6 grams per liter of dissolved zinc and 150 to 200 milligrams per liter of copper. The zinc is moving down through the tailings, but the copper is attenuated by formation of this blue mineral here, covalite, on the surface of sphalerite. So we get enrichment of the copper within the profile. And then we move to the Wade Amulet tailings impoundment outside of Rouen and northern Quebec. And that's about 30% sulfide minerals and less than 5% carbonates, where there's acidic drainage and high concentrations of dissolved metals. So we applied a model that was developed by Greg Davis and Ian Ritchie at the Australian Nuclear Science and Technology Organization. So it's really an unreacted core within a rim of oxidized material. And that's really similar to what we saw in the field. This is a pyrrhotite grain with an iron oxide rim that surrounds it. And we see reasonably good agreement between our oxygen concentrations we measured in the field and our model predictions. And that leads to estimates of the duration of sulfide oxidation of between 150 and 640 years, which was far greater than the mining company has anticipated. They were looking at something on the order of 25 to 30 years. Our analytical tools were getting better. We acquired an ICP OES optical emission system. We could analyze 29 elements at a time. Data acquisition was computerized and our detection limits went down. We got a better ion chromatograph that was also computerized, and we expanded our list of titrations. And we developed a series of reactive transport models. So this is a diagram that was derived from this one developed by Charlie Alpers and Kirk Nordstrom in the late 1990s. So initially there was a series of chemical speciation mass transfer models developed, and by the mid to mid-1990s, those have been coupled to flow and transport models to develop reactive transport models. So the first one that we developed here was Mintech coupled to a 2D flow model that Emil Frinn's group had developed, and that was Mintran. After that, we added unsaturated flow and gas transport in the Vados zone to that, which code Mintox. And then there was a quantum leap in our reactive transport modeling from a model that was developed by Uli Meyer, Min3P, and has been continuously revised since he developed it. So that's really our code of choice now, and there's parallel versions now that make simulations much more rapid. We did a series of studies in the Sudbury area. Part of the rationale for doing these studies is because Will Robertson came from the Sudbury area and knew the tailings impoundments well. This is the Nickel Rim tailings area that's on the edge of the Sudbury Basin. This is an aerial view that shows a cross-section from A to A prime, and these are the tailings that are well weathered. So Ray Johnson studied the water chemistry within the tailings impoundment, and Jeff Bain studied the plume that was emanating from the tailings into an unconfined aquifer below. So there's low pH conditions at the surface where sulfide minerals have oxidized, then that water is moving through, and you can see the sulfate plume moving through the tailings, beneath the dam, and into the aquifer. And then there's recharge of surface water downstream in a small pond, which causes additional acidification down here in low pH conditions. And the high iron concentrations are also moving through the aquifer. So as Uli Meyer simulated this with Min3P, and you can see the simulation results compared to the measurements. And it's quite good agreement in the pH, the concentrations of sulfate and iron, the concentrations of nickel and copper, calcium and magnesium derived from acid neutralization reactions, and sodium, potassium, silicon, aluminum derived from aluminosilicate dissolution. One of the key outcomes of this, the modeling was that the tailings were deposited ending in 1955, and we were doing our work in the early 1990s. So almost all of the oxidation reactions had finished. So it was really too late to try and prevent those oxidation reactions, so we shifted our attention to looking at treating the aquifer, the contaminated water within the aquifer. So we installed a permeable reactive barrier within the aquifer to treat the plume water, and that was composed of organic carbon, and this formed the basis for a study conducted by Sean Benner. So we installed the barrier in 1995, and we modeled it annually until 2003. So this is the barrier that's here. It's composed of really municipal compost and wood chips mixed with pea gravel to maintain the hydraulic conductivity, and the water flows from this side to this side and gets treated on its way through. We saw quite good treatment, so sulfate concentrations declined by about 50%. The iron is removed from the water, and the acid generating potential is removed. So water that has a strong acid generating potential on this side becomes acid consuming as it moves through the barrier. And we saw a variety of different iron sulfides. So initially there was poorly crystalline ferrous sulfide, and then more crystalline iron sulfide minerals like greigite, and we saw the occurrence of elemental nickel. So Uli also simulated the performance of this barrier, and the smooth curve is here. And these are measurements that were made over the course of the first few years. So we see a few things. One is there's a really rapid decline in the performance of the barrier in the first year as the more labile organic carbon is being consumed. And then there's an annual fluctuation in the degree of treatment that's really associated with the change in temperature that we see throughout the year. Our tools got better again. We acquired a ICP OES system, a new one, an ICP-MS, a high-resolution ICP-MS, and a multi-collector ICP-MS for looking at metal isotopes. Our ion chromatographs gave us greater versatility, and we started looking at 16S RNA amplicon sequencing for microbial communities characterization. We advanced our mineralogical tools. At Waterloo, we developed, the lab facility was developed. It's a variety of SEMs and spectroscopy techniques. And we started using the synchrotrons both in Argonne National Lab near Chicago and at the Canadian Light Source. So that gives us the oxidation state and speciation of metals or elements in the system, and also a lot of information on the structure and the nearest neighbors of ions. So those have become a really critical part of our work. So we went back to nickel rim 26 years later, and this is work that was done by Austin Miller. And he saw a decrease in the sulfate concentrations, similar to what was seen when the barrier was first installed, a decrease in dissolved iron, near complete removal of nickel, and the PRB discharge, the barrier discharge, had little or no potential to generate acid. So it was still performing the way that it had been about 25 years earlier. When we looked at the microbial community, this is the microbial communities are sulfate-reducing bacteria upgradient within the barrier and then downgrading the barrier. So in all cases, sulfate-reducing bacteria are abundant, but the abundance and diversity of bacteria within the barrier is greater than upgraded or downgradient. And we see shifts in carbon and sulfur isotope signatures that are really consistent with bacterial sulfate reduction. Austin compared his measurements to those made right after the barrier was installed and about 3 years after the barrier was installed. And he saw rates of sulfate removal that were similar to what was measured in the early 2000s, and removal of iron that's about the same rates. So the high rates were sustained for more than 26 years after the barrier was installed, which was much longer than our anticipated lifespan, which was somewhere between 10 and 15 years. And the removal or sulfate removal ratio is to iron is about 1.8 to 1, which is what we'd expect for pyrite. Then we move to the other side of the basin, to the Coppercliff central tailings area. So this is near the town of Coppercliff, which is right here, adjacent to the community of Lively, which is the hometown of Will Robertson. And so we did 2 transects, one from A to A prime, which we sampled earlier, and then one from B to B prime, which was the basis for Andrea Brookfield's master's thesis. So Will had done a really detailed analysis of tritium and movement in an aquifer near Sturgeon Falls, and he applied the same techniques to the Coppercliff tailings area. So you see the peak concentrations of tritium in the middle of the tailings impoundment, and that was tritium that was derived from atmospheric testing in the early 1960s. And so we knew that that water was pretty much between 1963 and 1965. And that was moving down through the tailings impoundment into an aquifer underneath, or else discharging to the surface water flow system that's here. We looked at the sulfate concentrations. They were following the same pattern. So Chris Coggins, who's a master's student, coupled the flow systems characterization with some sulfide oxidation modeling to predict the concentrations of iron that would hit that plane where water would be discharging. So we anticipate seeing a sharp increase in the concentrations in the effluent right about now, and then a decline in concentration over about 350 years, and another rise after about 400 years, and then a subsequent decline. So we first saw this as very depressing, that something that had occurred over the course of 25 or 30 years is going to have an impact for several centuries. It took me a while to get over that. So we went back after 22 years and we looked at what was going on to kind of check up on the progress and the applicability of our calculations. So we see the same style of oxidation as described by the shrinking core model. These are the simulations that were conducted looking at oxidation in 1991 and 92. And this is oxidation or oxygen penetration in 2014. And we see depletion of sulfides initially in 1991 to 92 to here, and in 2014 and 2015 down to about here, which is consistent with the model calculations. So we think that those calculations are appropriate. So work was done by Justin Buis, who is standing here. And you can see depletion of the sulfide minerals, or copper in this point. And the aqueous concentrations rise sharply where it's being depleted, copper is being depleted and then decline due to the formation of covellite. And we looked at copper isotope ratios. We see a sharp change rising, sharply rising where copper is being removed from solution. So the copper isotope ratios are a really sensitive indicator of the reaction mechanism and progress that's going on. And this is another profile where, again, we see the declining concentration and enrichment of the copper 65 isotope ratio. So we applied different isotope measurements to different field settings. So so we use copper, nickel, zinc, selenium, chromium. So this is what we see for zinc. So if you precipitate zinc as a zinc sulfide, for example, sphalerite, you get isotope trends going one direction. If you precipitate zinc carbonate, you get isotope trends going a different direction. So it's a really good indicator of what reactions are controlling the concentrations of dissolved metals within an aquifer. So we vastly expanded our field projects to a number of different sites across Canada and throughout the world. And after the work that we did on the nickel rim reactive barrier, almost all of our projects included a remediation component, which is rewarding. We looked at a composite cover at the Camp Koshia mine outside of Timmins. So Camp Koshia is just about here on the edge of Timmins. And there's two tailings impoundments. One is north impounded tailings, where there's a tailings dam that surrounds the tailings, and the second is the unimpounded tailings impoundment that's located here. And the impounded tailings impoundment was covered with a composite cover to try and lessen infiltration and sulfide mineral oxidation. So this is just a little video of the tailings impoundment. So this is the unimpounded tailings here that's extensively oxidized. And then off to the side are the impounded tailings. Sorry, the first was the unimpounded tailings. And that's has a composite cover and has been revegetated. The concept of the cover, this is from 3 locations where we did sampling, is a sand layer on top of a clay layer with a geosynthetic clay liner underneath it, and then another sand layer, then a layer of waste rock, which is intended to form a capillary barrier. So the intention is that the clay layer maintains moisture and limits water flow and gas transport, and that the capillary barrier limits water transport through the system. At one section, we see an organic carbon-rich peat layer that's down at the base of the stratigraphy. So the contractors came and pulled back the cover, and so we can install instruments within the tailings and within the cover system. And we collected cores and installed a variety of different instrumentation. Then the cover was replaced. The geosynthetic clay liner was reintroduced or reinstalled. Data loggers were hooked up, and we started making measurements. So this is Arya Zhang in the Bug Hood, who did her master's thesis on this project. So we look at the gas fluxes. At 2 sites, KK3 and KK5, we see sharp declines in the oxygen concentration and increases in the carbon dioxide concentration. So carbon dioxide goes up to about 10% of the volume percent of the gas, and the oxygen concentration declines sharply. And that's at these two locations. At KK4, we see a seasonal variation. So in the springtime, the oxygen flux is low, but in the late fall and early winter, the oxygen flux is high. So the cover system is draining, and oxygen is allowed to, or is able to penetrate through the system. So we looked at how the cover would perform, or what the system would be like with and without the cover. So with the cover, the oxygen flux, even in the partially covered system, is about 0.5 grams per meter squared per year. And in uncovered, it would be 2,000 meters squared per year to 4,000 meters squared per year. And that's had a profound effect on the water quality. So below the cover, the pH is near neutral. The concentrations of sulfate are moderate. Concentrations of things like iron and copper are low, but we see elevated concentrations of things like arsenic and zinc. In the organic carbon-rich layer below the tailings, we see sulfate reduction, bacterially-mediated sulfate reduction. That removes the sulfate from the water, decreases the iron concentrations, removes the arsenic and zinc from the water, and that's followed by reductive dissolution of iron oxides and manganese oxides, which results in an increase in dissolved iron and a increase in dissolved manganese. And we looked at the Yellowknife, or sorry, the giant mine in Yellowknife, and that operated from 1948 to 1999, and then was closed permanently in 2005, and is now the responsibility of the Government of Canada. There's a legacy of contaminants at the site. The most notorious is 237,000 tons of arsenic trioxide stored in vaults and chambers in the underground, about 500 meters from Great Slave Lake. So that's continuously pumped, and the plan is to freeze those chambers and try and retain the arsenic in place that way. We have another project looking at other ways of stabilizing that. There's about 16 million tons of tailings stored above ground, which are a complex mixture of arsenic-containing flotation tailings and calcium roaster waste, and a small component of this arsenic roaster waste that came from the baghouse. So the hydrology here is complex. The tailings impoundment is used as a storage area for water throughout the year. So in the springtime and over the winter, water is stored on the top of the tailings impoundment, and then it's gradually drained off and treated. And then in the wintertime, again, they start adding water to the pond. So there's a cyclical change in the volume of water in the pond, which really affects the hydrology and the biogeochemical processes that are occurring. So these are two cross sections from C to C prime across the long axis of the tailings impoundment, and from B to B prime across the short axis, which is here. Adjacent to the dam, the water table stays relatively high throughout the year, but adjacent, or in the transverse to that, is this section where there's a sharp decline in the water table as you move over to the east. And that's because there's recharge moving through the base of the impoundment, through a fractured rock zone and into the underground workings. So drainage water from the pond and the tailings goes through the tailings, into the fractured rock, and into the underground workings, where it's pumped up and then put back on the tailings impoundment. So there's kind of a perpetual cycle going there. When we look at the sulfide oxidation, oxygen is penetrating down to about 4 meters. And that's because the sulfide content is quite low, less than about 0.5% sulfide. But it's still generating high concentrations of CO2, which are diffusing upward from the tailings into the atmosphere. These are two locations where the water table is deep, and you get extensive oxidation at depth. Where the water table is shallow, the oxidation is limited to the near surface area, near surface zone. So because of the sulfide oxidation, and then also the development of the recharge pond, or pond recharge from the pond, arsenic and antimony, which are the two principal contaminants here, have different behaviors. So arsenic is derived from both oxidation of sulfide minerals within the unsaturated zone, but also from the pond water and reductive dissolution of arsenic oxides, arsenic-bearing iron oxides within the tailings area. So we see the highest concentrations of arsenic within the center of the tailings impoundment. In contrast, we see the highest concentrations of antimony in the vadose zone where sulfide oxidation is occurring. So there's two different types of behavior. We looked at the microbial community structure. In the location where the water table is deep, there's an abundance of iron oxidizing bacteria. There's less iron oxidizing bacteria where the water table is shallow. We see the occurrence of iron or sulfate reducing bacteria after oxygen is being consumed, deeper in the location where the water table is deep, but sulfate reducing bacteria are abundant throughout the entire profile where the water table is shallow. So over the course of several years, we developed a conceptual model of this system. This is a diagram from Maria Friada-Espinosa, and she's taken data from microbiological data from Eva Pakistova and geochemistry data from David Hilger. So we see in the vadose zone oxidation of arsenopyrite, which generates ferric oxyhydroxides and ferric arsenates, and iron is being oxidized from ferrous to ferric, and arsenic is being oxidized from arsenic 3+ to arsenic 5+, and precipitating as this mineral. And sulfur is being oxidized and released as sulfate. Below the water table, where there's an abundance of these arsenic-bearing iron oxides, maghemite and hematite, that's reductively dissolved by iron-reducing bacteria, and that's releasing CO2 plus iron and arsenic. So that's resulting in the accumulation of ferrous carbonate or siderite and iron sulfides, or FES. At the same time, sulfate is being reduced by the action of the sulfate-reducing bacteria. Some of the arsenic is incorporated within the iron sulfides, but much of it is transported through the water column. So infiltration that enters here goes through the oxidized zone and through the reduced zone, so accumulating arsenic along the flow path, and then enters the fractured rock flow system and then into the underground workings. So this is a comparison of field data that was measured by David Hilger and simulations that were conducted by Maria Espinosa, or Friada Espinosa. So on the top, we see the effective neutralization mechanisms. So the pH is near neutral. There's calcium and magnesium that are derived from carbonate mineral dissolution. Below that, there's release of, below that in the diagram, but above that in the tailings impoundment, there's release of metals through sulfide mineral oxidation in the vadose zone. And beneath that, there's release of arsenic to the tailings pore water through reductive dissolution of the iron and manganese or iron oxides that contain arsenic. So that's where the greatest accumulation of arsenic occurs, in the pore water. So we've also looked at waste rock. This is a conceptual diagram of waste rock evolution that was developed by Ian Ritchie. So this is a waste rock pile. There's rainfall infiltration into the surface and oxygen diffusion, but there's also potential for oxygen to enter the sides just through the wind-blown advection, but also because sulfide oxidation is strongly exothermic, we get heat building up in the pile, and that's resulting in the development of convection cells that draw oxygen in from the sides of the pile. So a lot of the pile is oxidized and releasing contaminants at the same time. So a little video of waste rock deposition. And really what's important about this is you can see big chunks of rock rolling down to the base of the pile and accumulating in a rubble zone down there, which is important in terms of gas transport. So this is a conceptual model of that system that was developed by Ward Wilson from Alberta. And so you end up with this rubble zone at the base of the pile, and after sulfide oxidation gets started and things start to heat up, this draws oxygen into the pile, so much of the pile is oxidizing at the same time. We did, as Scott mentioned, we did a long study at the Diavik Diamond Mine in the Northwest Territories. So that's where Diavik is, on the shore of Lac de Gras, or on an island in Lac de Gras. So this is the mine that's here. There's 2 open pits at this time. There's a waste rock pile that was waste rock from the open pits, and our little test facility is located over here. Diavik is cold. So the temperature varies from about minus 40 to about plus 25, but for much of the year it's below freezing. The waste rock at Diavik is really low in sulfide content, so Diavik segregated its waste rock into two types. Initially there was 3 types, but it's reduced to 2. So type 1 has less than 0.04 weight percent sulfide, so very low sulfide content. And the type 3 rock, which is the more acid-generating rock, only has a sulfide content of 0.08 weight percent sulfide. So that's in contrast to the much higher sulfide contents that we've seen almost everywhere else. In addition, there's a tonalite, which is a intrusive mineral or intrusive rock that has a much lower sulfide content than either the type 3 or the type 1 rock. And this is the pit walls, and you can see these black zones within the pit walls, and those are the sulfide-bearing biotite schist that is randomly distributed within the granite. So we constructed a field research facility at Diavik, and that has 3 waste rock piles, one with type 1 waste rock, one with type 3 waste rock, and one that tests or evaluates the closure cover design, which is 3 meters of benign type 1 rock, then 1.5 meters of till, and then the waste rock underneath that. So the objective is for the 1.5 meters of till to freeze and form a thermal barrier, or a frozen barrier, and then the 3 meters of low sulfide rock is intended to be a thermal barrier that keeps that layer frozen. In addition, we have a series of lysimeters near the top of the pile, which go down to about 2 meters deep and are built within a platform that's here, so we can look at just the very shallow portion of the pile. And part of the objective was this, that we were building this, it was so cold we weren't sure we were ever going to see water at the bottom. So we built these lysimeters just in case, so we still have a research project. But we did see water at the bottom, which is good. And then we installed a large variety of different instrumentation. We installed tensiometers and moisture content sensors for looking at the hydraulic head and and moisture content versus depth. We collected samples from the upper lysimeters. We had measurements of temperature and thermal conductivity in the rock, measurements of the gas permeability of the rock material, automated measurements of the gas pressure and concentrations. We collected the effluent from the bottom of the pile and also from a series of lysimeters within the pile. We looked at the microbiology. We collected water samples from suction lysimeters or soil water solution samplers versus depth within the pile, and then looked at a variety of lysimeters, water chemistry from a variety of lysimeters within the pile. In addition, we did a series of laboratory experiments based on a conventional technique that's used for evaluating the potential for acid rock drainage from mining companies, and part of the goal of that was to see if we could scale that to larger scale systems, or full-scale systems. So we did 18 of those experiments at room temperature and 8 in the cold room to look at the temperature dependence of the reaction rate. And we installed instruments in the full-scale waste rock pile as it was being constructed. Early on, we did a couple of tracer tests to look at water flow through the pile. So we did a deuterium tracer test, and that was followed by a chloride bromide tracer test. And those were done on the top of the pile as opposed to the sides. And you can see these sprinklers that are here, and that's how we're applying the tracer. In addition, we recognized after a while that there was resident tracer in the system. So the rock is blown up in order to excavate it to get to the structures. So the rock is blown up in order to get to a manageable size, and so that uses explosives. So these are videos at them. So we were trying to find a way to get some pictures of this, and it turns out the company that was producing the explosives was constantly making videos of the explosions so they could see how well their fragmentation was working. So after weeks of trying to finagle a way to get a picture of the waste rock or the rock blowing up, they just gave us a bunch of videos. So it was pretty nice. So the explosive they use is a combination of ammonium nitrate and fuel oil, and They use perchlorate as an accelerant, so that's like the blasting cap for initiating the explosion. So the residual waste rock contains ammonia, or the waste rock contains residues of the ammonia, the nitrate, and perchlorate. And we use those as tracers as well. So we looked at data going through the pile. We have a variety of different measurements. We can take samples from the soil water solution samplers versus depth. And then we can collect water samples from these collection life simmers that we have at the base of the pile. And then we can collect samples, trying to get one more here. We can collect samples from the drainage system at the base of the pile that's here. So we could follow the tracer system, tracers going through the pile. So this is the chloride from the year after the tracer test started, then 3 years after, 5 years after, and then by 2015, the tracer had moved all the way through the pile. In addition, so that's bromide. We see the same thing for chloride. And we look at the blasting residuals, we can see them also migrating through the pile. So we have 3 or 4 independent tracers that look at the velocity of water going through the system. So this is work that was presented by Sean Sinclair. So in addition to these blasting residuals, we see perchlorate. So perchlorate is ClO4-. It's only derived from blasting. There's no natural source in this area. And we could trace the fingerprint of the blasting from Diavik and from the Acadie mine, which is a few kilometers away, throughout the entire Lake Lac de Gras. So it's a really good tracer. You can see the progress of the oxidation of sulfide minerals and weathering. So when we first started, the pH was neutral throughout the pile. And over the course of about 8 years, the pH fell to between 3.5 and 4.5 throughout the depth of the pile. And that was accompanied by the depletion of alkalinity, so all the buffering capacity has been removed, and an increase in the concentration of dissolved aluminum from very low concentrations up to about 80 milligrams per liter. And the iron concentrations were increasing, but not as drastically. We also see high concentrations of sulfate increasing over time. The sulfate concentrations are controlled by solubility with respect to gypsum, but the dissolved nickel concentrations increased from relatively low concentrations up to about 30 milligrams per liter, even at a very low sulfide content. So this is measurements from the basal drains of the type 3 pile, and they show a trend over the course of the years. So individual years plus the years. So we see high pHs every year at the beginning of the year, and that's water that's coming through the edges of the pile and really doesn't contact much sulfide mineral. And then as time goes on, more and more of the center of the pile starts reporting to the drain, and so the pH falls every year, and we see a decline in alkalinity that occurs every year and an increase in dissolved sulfate. We also see the similar increase in dissolved nickel, cobalt, and somewhat of an increase in dissolved iron. Most of the iron is precipitated as iron oxides within the pile. So David Wilson did some scale-up studies, a scale-up study based on the laboratory experiments, this medium-scale field experiment and the large-scale field experiment, and he tried to see if it was possible to scale these experiments to try and get results that are similar to what we see in the large-scale experiments. So he used Min3P, the reactive transport model, or the current version of Min3P, and tried to scale things to get an estimate of the variation in the large-scale pile based on the humidity cell tests. So these are simulations of the humidity cells, which agree with the lab data reasonably well. The active zone lysimeters, which show fluctuations similar to what we see in the field, and then the large test pile. So with only adjusting the parameters that are typical of each rock, so the rock that's in the humidity cell wasn't exactly the same as in the test pile, but when you take rock composition that's similar to what's in the test pile, you get results that are similar to what we see in the field. So it is reasonable to try and do that scaling. And this is just more simulation showing nickel, cobalt, copper, and alkalinity. After, in 2014, we deconstructed the large, or the type 1 test pile to look how things were changing inside of it. So we We got some equipment from the mining company, and they dismantled the pile from us. They told us it would take about 3 weeks to do it, so we had to get a big crew there so that we didn't waste their time. So we got lots of people there, and it ended up taking much longer than they expected. So you can see as time goes on, the days get shorter and the nights get longer. And as we take the pile apart, we were collecting samples from within the pile for mineralogical characterization, for looking at the bacterial or microbial community, and extracting pore water to look at the pore water composition. So we ended up with 2 trenches along the length of the pile, with 2 transects across the pile where we had really detailed measurements of water chemistry and mineralogy. So this shows the acid neutralization potential. So this is a method of looking at the potential to generate acidity. So values of less than 1 have the potential to generate acidity. Anything that's more than 2.5 is expected to be neutral in pH. So most of the pile is neutral. There's a zone up here that has potential to generate acidity, and we look at the pH, that zone does generate acidity, as well as a zone at the base of the pile. And we see elevated nickel concentrations in the zone that's become acidic. We see depletion of alkalinity concentrations that are mostly high within the pile, but at the zone where there's low pH conditions, the alkalinity is depleted. And sulfate is relatively high throughout the pile and is controlled by equilibrium with respect to gypsum. This shows nickel again, then cobalt and zinc concentrations, which are highest in the zone where the rock is acidified. So the closure design for Diavik is this layered system. So with the benign rock, and then the frozen till, and then the rock underneath it. And this is the implementation of that cover system. So after the open pits were excavated, the waste rock was in this pile. It was recontoured, and then the till layer was put in place, followed by the tonalite layer cover. And you can see the recontoured rock, waste rock pile in the background. And now the caribou have repopulated the pile now. We also looked at the Faro mine complex in the Yukon, which is just outside of the town of Faro. And that's a zinc mine that went bankrupt in 1998. And it's also controlled by the government of Canada. And there's both waste rock and mill tailings here. So in this diagram, or this photo, you can see the Faro pit, which is now flooded, the waste rock piles that surround it, and this is the one that we're studying, and then the tailings impoundment in the background. So this is the pre-mining surface where the waste rock was placed on top, and then the waste rock was placed on the top of that surface. We installed a series of instruments using boreholes. So we have soil water solution samplers for measuring water chemistry, gas sampling ports for looking at gas concentrations of oxygen, CO2, and nitrogen, and argon. We have measurements of gas permeability and temperature, electrical conductivity, and moisture content probes. And then we have measurements of gas permeability. And so those are within these instrumented boreholes. And we constructed our boreholes, or installed our boreholes along a line that included boreholes that were installed previously by other groups, primarily to look at gas concentrations and temperature. So we have a pretty good profile going through the waste rock pile of different types of measurements. And then we're looking at different scales, going from the micron or nano scale up to the tens of meter scale, looking at hydrology, geochemistry, microbiology, and mineralogy, and then we're initiating reactive transport simulations now. Hydrology is affected by surface water runoff, which flows on the surface of the pile. There's residual pools of acidic water that accumulate. There's areas of fine-grained material where infiltration is slow, and then there's zones of cavernous rock where infiltration is preferentially more rapid. So we simulated the recharge using just the Penman-Monteith model, and you can see the variation in infiltration. So in some years it's relatively high, and other years it's relatively low. It's very low. And depending on the year, our estimate indicates that up to about 1/3 of the precipitation infiltrates. So it's variable, but there is a significant amount of infiltration. These show depth profiles of oxygen concentrations, so oxygen is being consumed, CO2 is being generated and diffusing upward or moving upward. The moisture content is relatively uniform throughout the depth, and we measured O18 and deuterium concentrations or ratios throughout the pile, and we see a few things. We see the seasonal variability in recharge, so the lighter isotopes in the wintertime, heavier isotopes in the summer. But we also see enrichment at about this depth, which we attribute to evaporation that's occurring due to the high temperatures within the pile. So we see a zone of evaporation within the pile, and that evaporated vapor is moving with the gas that's moving through the pile. The mineralogy is complicated and interesting. There's lots of different sulfide minerals. Pyrrhotite is the most common sulfide mineral, but there's lead sulfide, galena, zinc sulfide, sphalerite, chalcopyrite, and as well as some pyrite. So there's lots of different elements in the water. There's a variety of different sulfur salts that have things like molybdenum, antimony, selenium substituted into them, so it's a real cornucopia of dissolved metals. When the pile was developed, they selectively placed the sulfide rock at different layers within the pile. So the idea, I think, or I've been told, is that this more benign rock on the top would isolate the more reactive rock deeper in the pile. So you can see the high sulfur and iron content here, which is the sulfide-rich zone, with higher levels of zinc and lead. And those layers are at different levels in our different boreholes. So unfortunately, this wasn't a successful strategy, but it's good for a field experiment. So we see high concentrations of dissolved metals. This is iron and sulfate here, lead and zinc, arsenic, that occur within this zone of high concentrations of sulfide minerals. So we look at the discharge from the pile. We see discharge coming through here to these wells that are at the base of the pile and also to the surface water flow system. So that's down here on the edge of the receiving water body. And over time, CERNAC, which is the government agency that controls the site, has been making continuous measurements of the concentrations at those two locations. So we see over the metal with the highest concentrations of zinc is zinc. It's a zinc mine, which is in the tens to hundreds of milligrams per liter. And then concentrations of iron, nickel, and cobalt. Then slightly increasing concentrations of cadmium. But the concentrations of copper and lead are rising progressively. So the reason for that is as time goes on, initially the mineral that controls the concentration of lead is a lead carbonate, which is relatively insoluble. It's a mineral called shannonite that retains low concentrations of lead in the effluent. As the pH falls, the water becomes undersaturated with respect to the lead carbonate, it dissolves, and it's replaced by a lead sulfate, which is much more soluble. So we'll start to see these lead and copper is retained on the surface of the lead sulfide. So we'll start to see those concentrations rise more quickly than the other metals. Okay, so there's a variety of different challenges associated with what we're going forward. The biggest challenge that I see right now is that there's been a real sea change in attitudes towards the mining industry and the stability of tailings dams. So there was a variety or a series of catastrophic dam failures in the mid-2010s, say 2013 to 2015, and that was devastating. So the institutional investors who support the mining industry, one of the largest with is the Church of England, got together and decided, this wasn't something they would tolerate anymore. So there's been a real focus on maintaining the stability of tailings dams and enhancing their structures. Most of these failures were due to foundational failures, not failures within the tailings dam itself. So the foundation fails, and the tailings run out through the dam after it fails. So the strategy for maintaining or preventing sulfide oxidation over the last couple decades has been to maintain a higher water table and limit oxygen ingress, which results in more tailings being susceptible to flowing, and increases the runout distance. So more of the watershed is impacted by the tailings if you maintain a higher moisture content. It doesn't cause the failure, but it exacerbates the effect of the failure. So there's a variety of strategies that are being developed to address that. And there's more strict regulatory compliance for maintaining moisture content within tailings dams. And there's a global industry standard for tailings management, which really focuses on maintaining unsaturated conditions within tailings impoundments to maintain dam stability, which has the effect of increasing the release of acidic drainage. There's some potential solutions. So a real strategy that's used widely now is to take as much of the sulfide out as you can and putting in paste backfill in the underground where it's constantly submerged and won't cause as much damage. There's a focus on thickened or dry stack tailings where you stack the tailings in a dry state, and the objective of that is so it's always stable and won't fall down. And that's has the potential of generating very low moisture contents and then exacerbating the acid generation problems. And then there's a strategy of mixing waste rock and tailings together. So this is paste rock, which is a mixture of tailings and waste rock, which if the waste rock is self-contacting, then that stays stable. And the tailings fill the voids, which limit the advective gas transport through the rock. So this is a concept that was proposed by Ward Wilson from the University of Alberta 2 decades ago and has really gained popularity in the last 2 to 5 years. There's also the challenges associated with the development of critical mineral deposits. If you watch the news, you'll see that there's a big focus on developing critical minerals. There's a big ad from the Ontario government, not the one about Ronald Reagan, but one about critical mineral development in the Ring of Fire. And so that has potential to support the development of low carbon energy sources, but also has the potential to generate waste streams that we're not familiar with. And so the need to develop strategies to address those types of wastes. There's also potential to recover mineral resources or critical mineral resources from existing mine waste, either from dissolved constituents within plumes or in the surface water flow system, or from extracting the waste from those minerals from waste where they weren't the target elements in the first place. So we look at tailings impoundments that we've worked on through the years. There is potential in some cases to extract elements from those that weren't the target of the initial processing. So if you reprocess the tailings, then there's an opportunity to do a better job of disposing of the waste and protecting the environment. Okay, so I'm at the end. So there's lots of people I need to thank, many people. Carol Potashnik's been a co-investigator on most of the work that we've done. Jeff Bain and I have worked together for more than 20 years. I mentioned John Jambor before. We've had lots of collaborators from Waterloo and from other institutions around Canada and the world. We've had a huge number of dedicated staff members who we're very grateful to. Lots of postdocs, graduate students, undergrads, and co-op students. We constantly employ undergraduate students. We get great support from the mining companies at the mine sites and from the government at sites that are managed by the government. And so we're very grateful to all of them. We've had good support from the mining industry and from government agencies. And so I'll take any questions that you may have.